Hi everybody, welcome back to Chem 121. It's been a long weekend, and I hope everybody is refreshed and relaxed. I'm sure not. I didn't get much sleep this weekend for whatever reason. So we're going to continue with Chapter 7, but for announcements, last call for Chapter 6 quiz is tonight. Make sure you get that in by the deadline before it closes at 11:59. We're going to finish Chapter 7 today, most likely. Let me find my slides. Here we go. And last we left off, as far as I'm aware, was right around here. We were talking about boiling point. And we were drawing a diagram of the atmosphere above us and how it pushes down with its weight to create a pressure. And when it does that, at sea level, we call that atmospheric pressure, equal to 1 atm. Now, when water is boiled, it needs to push against that pressure in order for the liquid to turn into a gas. And the temperature at which that happens is the temperature at which the vapor pressure of the liquid, in this case water, equals or exceeds that, well, just equals, it will exceed it at a higher temperature, equals that of the atmospheric pressure. Alright, so I have these 3 problems on the screen here. I don't think that we got to do them. Rather than go back and look at the previous video myself and see if we did them, I'm just going to start here and do these problems. And if you want to try them, you can always pause the video. That's fine. But let's go over here, and we'll just knock these right out. Alright, so let's draw... hold on, I had to change all the colors because I was working in Photoshop again. Boop. There we go. So let's draw our little picture here. So here is our atmosphere. That's not a drawing, that is the select tool. There we go. I don't like this pen that I've selected. There we go, that's much better. Alright, so here's our atmosphere up here along the top. And then here's the ground or whatever, and then here's the ocean. Like that. And so if we're here at sea level, then the pressure of the atmosphere pushing down is 1 atmosphere. And so we said all that earlier. And so now what we're going to do is we're going to look at various liquids. So we have liquid A. And its vapor pressure equals 760 torr at room temp, which we're going to just call 25 degrees Celsius. That's close enough. All right. Will liquid A boil? Remember, a liquid will boil. We'll just zoom this in here. If its vapor pressure is equal to that of the atmosphere. And this would be my vapor exerting a pressure against the atmosphere, which is not shown or drawn. So what is PATM equal to? Well, it's equal to 1 atmosphere. But we also said that if we go back and we look over here at... I gotta find which slide it is. Oh, it must be way up here. Yeah, there we go, way over there. Oops, sorry, that's not the button I meant to hit. I don't have a cursor is my issue here, so I'm trying to find it. Sorry, give me just a second. Technical difficulties. There we go. That's better. I can see where I'm pointing now. If we look at this slide here, you might remember that this definition exists. 1 atmosphere of pressure is the same as saying 760 torr of pressure. So now if we go back to the slide that we were on, that's the wrong slide. There we go. We can see, hey, our pressure is currently 760, which is equal to 1 atmosphere. So since this is equal to atmospheric pressure, then we would conclude that liquid A would boil at that temperature because it currently has enough vapor pressure to boil. Now let's look at liquid B. Its vapor pressure is far less than 760. Now, what is this in ATM? Well, we could do this, right? So we could calculate what its pressure is in ATM, just so we could compare it that way, if you wanted to. You could also just say 216 is less than 760. All right, so this is the pressure for liquid B. So up here in this diagram up at the top that's kind of cut off, we'll put it right here. So this would be 0.284 ATM, and this would be 1 ATM. Now, this number is not equal to or greater than that number. And so the result that we would conclude is that since this is less, we would say liquid B won't boil at the temperature that we have. And in order for it to boil, you need it to be a little bit hotter. In fact, you need it to be a lot harder. Just for reference, in case you were curious, water's vapor pressure at room temperature, again, we're using 25 Celsius here, that's a little bit high, but that's okay, is roughly like 30 torr. So water does not have a vapor pressure anywhere near atmospheric pressure at room temperature. So it does not boil. Now, if liquids boil, they turn from a solid, or not solid, I'm sorry, a liquid to a gas, right? But doesn't that happen anyway at room temperature? And the answer is sure, but what's actually happening at room temperature is this is our liquid, and here are our molecules right here. We called this process evaporation. And it's different from boiling because what can actually happen is if the container was closed, for instance, then what would happen is that my liquid would recoalesce from particles that are bouncing around in the vapor phase. And so at some point we would reach a saturation in here. You can see this process in action if you have some sort of bottle or closed container that has something hot in it. And that hot substance may or may not have water that is trying to evaporate as either as steam or at least very high temperature water relative to room temperature. So like I see this when I'm cooking things like rice or chicken, and then I put it in a Tupperware with a clear top. all the water condenses on the side and turns into the liquid phase again, and it gets all foggy, right? That is the steam or water vapor turning back into liquid water. And because the water's inclination is to do that and stay in the liquid phase, and it is preferred to be in the liquid phase in terms of energy, that we don't call this process at a lower temperature boiling. It's just evaporation. Evaporation is an exchange with the gas phase from the liquid phase, but it's not the preferred phase in the gas phase. The vast majority of your substance will stay as liquid water until you have the vapor pressure equal the atmospheric pressure. So up here, for example, when these two forces are equal to each other, then the liquid vigorously boils. Now, just as a curiosity, what happens if you do this? If I open the container, what ends up happening is that my particles then escape and the odds of them coming back into the container and recombining as a liquid are so low just because once they get out into the atmosphere, there are so many different other places to go, and the odds of them randomly returning to the container are essentially zero. So if you leave a cup of water out on your countertop, it will eventually evaporate away. However, we do not want to call that process boiling because the preferred state of water at that temperature is to be a liquid based on how much vapor pressure it has. All right, for this last problem here, I have a bunch of vapor pressures, and I want you to arrange them from lowest to highest boiling point. And so it's very important to remember how vapor pressure affects boiling point. And so if the vapor pressure is high, then remember that indicates that the molecules in the solution or in the liquid oops, you can't read that because I'm writing behind the thing. Excuse me. Excuse me. If the vapor pressure is high, then the molecules in the liquid have weak interactions. And what that means is that if this is our liquid right here, here are my molecules in the water. If they have weak interactions between each other, then it's easy for them to escape. And thus they would have a high vapor pressure. And if the vapor pressure is high, that means that boiling is easier. Now, what happens if molecules have strong interactions? Then their vapor pressure is low, which indicates that the molecules will have strong interactions instead. So if these aren't really bonds, I just don't know how to draw them so that you could see them. And so they're all held together by these interactions. That means that it's much harder for the molecules to escape because they're bound to other molecules through these interactions. And since the vapor pressure is low, we have to heat it up higher. And so there's our two relationships. Something is a high vapor pressure, its boiling point is low. And if something has a low vapor pressure, its boiling point is high. So now we just have to sort these by vapor pressure. And so let's do that really quickly. So I've already got X and Z in torr. So 822. And then Y is in atmospheres. So in order to compare all these three things together, I'm going to just turn them all into torr. And then we can compare them together. And what did I get? 484. I don't know why I have two different looking 4s here, but it bugs me, so I'm going to just do that. All right, so let's sort these from highest boiling point to lowest boiling point. Well, the lower the vapor pressure, the higher the boiling point. So this would be the highest boiling point. I had to heat that one up the most. And then this right here, that's a very high vapor pressure, so it must have the lowest boiling point. Now you might look at this and say, wait a second, this is more than 1 atmosphere. What does that mean? Well, vapor pressure keeps going up if you go past the boiling point. And so if you have a number that's greater than 1 atmosphere, then what we conclude is that this boils at a temp lower than current. So whatever the current temperature is that you measured this vapor pressure at, its boiling point is lower than that temperature. So according to the problem statement up above, these are all vapor pressures at room temperature. And so if we went below room temperature, so like maybe like 20 or 15 or 10 Celsius or even 0 Celsius, this liquid would then boil. What are examples of liquids that have really low boiling points? Can you think of any? In fact, I showed you one last week when we were talking about gases. It was liquid nitrogen. Liquid nitrogen's boiling point is like minus 180 Celsius or something like that. It's very cold. And yet it is a gas at room temperature. Well, not and yet, but as a result of that, it is a gas at room temperature. And its vapor pressure at this temperature would be very, 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 very high. If you could have liquid nitrogen that had been heated to room temperature, its vapor pressure would be well above 760. And thus, once you immediately open the container, it would instantly start to boil. And that's why we refrigerate liquid nitrogen. All right. That was just a brief review on how to work with the concepts of vapor pressure and boiling. So now, actually, let me go back to this diagram really quickly. So when we were drawing this diagram, I was indicating things like molecules have strong interactions right here. What does this statement mean? Or this statement up here. What are these interactions? We've illustrated them as just being these like nebulous lines that I drew together. So what's going on here? And in fact, that's the entire point of this next section here. And as far as your biology class is concerned, this is probably the most important part of chemistry for that purpose. So Bio 211 cares very, very much about this topic, intermolecular forces. So this is kind of like the meat and potatoes factoid, I would say, of Chem 121. So we're going to do that today. This is going to be our focus for this time during the break, or up to the break, I should say. All right. On the screen, you're going to hear me open my, what do I have? I have Mandarin seltzer water today. On the screen, I have 2 HCl molecules, and I have a bunch of numbers, and I don't want you to worry about these units for now. I'm going to just scribble these out, so just ignore kilojoules per mole. That's not important to you. What these numbers are showing is what we're going to call, for now, just whatever the strength of the interaction that's indicated is. So here I have a bond. And bonds are strong because the number that we use to represent this is big. If I put in this much energy, I can break the bond. I can break the H and the Cl and separate them. Now, to take apart 2 HCl molecules that are attracted to each other, would be the intermolecular force that is holding them together. And compared to the bond, the intermolecular force is weak. So the intermolecular force is an attraction between molecules. Think of this as an attraction between a magnet and your refrigerator. You can pull the magnet from the fridge very easily. You just lift it off the fridge, but it tries to stick on its own, right? So the intermolecular force would be the magnet's attraction to the fridge, whereas the strength of the interaction for what we would call a bond in this case would be trying to pull the magnet itself apart. That's very difficult, right? You can't grab 2 sides of the magnet, specifically the magnetic part, and break it, right? You can't break the magnet very easily. But you can definitely pull the magnet off the fridge. That's not difficult to do. So we are going to represent these intermolecular forces in diagrams by just illustrating them as dotted lines. So when you see me drawing dotted lines, that is my intent to try and imply that these molecules are attracted to each other, kind of like if they were magnetic towards each other. Oh, excuse me. Now we're going to discuss the nature of this dotted line interaction, because it turns out that to some degree, all molecules and all matter is attracted to itself. Now, the nature of that interaction... Oh, excuse me, this is where my lack of sleep is going to catch up with me. The nature of the interaction is going to depend on the nature of the molecules present. And this is going to go back to chapter... When was it? Chapter 5, I would say. When we studied polarity. Remember that before the midterm? That feels like so long ago, doesn't it? We're already in week 8. Where did it all go? Almost at the end. Don't give up now. Anyway, back in chapter 5, one of the last things we talked about was polarity, and I asked you, tell me if the molecule is polar, yes or no. And from that would imply that you know what polarity means. It means that some of the electrons are on one side of the molecule more than the other, right? Because we drew that little vector diagram of, okay, we could draw all the bond polarity arrows, and we can shove the electrons along the arrows and see where they end up. Oh, they ended up on this side of the molecule more than the other. We did that. That force polarity is going to be very relevant here. Now, These interactions are what we were talking about in the sort of nebulous way in the previous section about boiling. These interactions hold our molecules together and affect boiling point. They also affect melting point, but we're not going to talk about melting point just yet. We're going to do that in chapter 8. 8 or 9, I forget which one. So on the bottom of the screen, I have two liquids. HCl boils at negative 85 Celsius. I'm talking about pure HCl here. Whereas pure H2O boils at 100 degrees Celsius. Which of the molecules are held together more strongly? HCl molecules towards each other or H2O molecules towards each other? Type which guess you think it is in the chat, and then we'll draw a picture and try and discuss it in just a second. Alright, hopefully you've had a second to think about this. So H2O is the correct answer. Now, why is that? Well, we'll just go back to this drawing we just did. And basically what we're going to be doing is working from the perspective instead now of how well do the molecules stick together. And what we can say is that if the molecules stick to each other well, i.e. they have strong interactions, then they can't escape to the vapor phase. And thus the boiling point would be higher. So, whichever one has the higher boiling point must have the stronger interactions. And so that's easy enough. We're just comparing two numbers. So which is bigger, 100 or negative 85? Well, clearly it's 100, right? So that liquid must have the stronger intermolecular forces. Now, these forces are constant. They're independent of temperature. So whatever the temperature of the liquid is, the magnitude of the attractive forces between molecules will remain roughly constant. What changes is how fast the molecules are moving. And so that's what boiling point is, because remember that temperature is just the speed limit for molecules, yeah? So if I have to get to 100 degrees Celsius for my molecules to boil, that means I need to make my molecules move that fast so that they stop sticking to each other. I think an analogy of this would be if you were throwing magnets parallel to your fridge's surface. So, like, you tried to, like, throw them past the surface of the fridge, but close enough that they could stick if they wanted to. If you throw it too fast, there's no opportunity for it to stick, and so it'll just sail right by the fridge. But if you throw it slow enough, it will attract to the fridge, bonk into the surface, and then kind of slide along a little bit before it stops on the surface of the fridge. So if you can make your molecules move faster, they don't stick to each other as effectively anymore, and then they can become a gas. So that's what we're going to be looking at here. We're going to be looking at the magnitude of these attractive forces. Now, the why here is going to be the whole point of this. Why do molecules stick to each other? And it turns out there is only one reason that is really relevant here. If I have a molecule that has an attractive force towards another molecule, this can only occur based on what parts of the molecule are present on the outside. And what did we say is on the outside of all matter? Whether this is an atom or whether it's a molecule, The outside region is just the electron cloud, right? Excuse me. And the electron cloud can have a charge that is either negative or partially negative. And if something can be partially negative on a molecule, then that must imply that there is a side that is more positive than that. And thus the attraction occurs between these opposite forces. If I have a side that is more negative than the other side, that implies that the other side is more positive. And a side that's more negative will be attracted to a side that's more positive. Even though they're both electrons, if there are few electrons on one side and many on the other, that's going to create a dipole and a potential for attraction. And that's what happens here. On the screen, I have, on the left for A is just a liquid, and on the left B is a solid. And you'll notice that they have a bunch of little pluses and minuses around them. The pluses and minuses within the molecules are intended to indicate partial charges. So this is delta plus, delta minus. This is delta plus, delta minus. And so on and so forth. Sorry, my cat is harassing me, and I don't know why. So, because I have molecules that have these dipoles on them, for example, maybe I had H2O. We'll just quickly draw H2O's Lewis structure. And then if I drew its dipole, its overall dipole would be something like this, right? Which would mean I could put a delta plus on this side and a delta minus on the other side. And that interaction, or that dipole, is permanent. Water just has this. And it has it all the time. And so what water molecules would do is they would align themselves in such a fashion that the negative part would always point towards a neighboring positive part. And they do this all over, as you can see in this diagram here for A. I just have a random assortment of molecules, but they try to arrange themselves such that they can maximize the attractions, but have the repulsions be as far apart as possible. So all the positives are as far apart from neighboring positives as they can be. In the solid phase, the molecules are able to do that very, very neatly, because that's what a solid is. It is an orderly arrangement of atoms or molecules. In the liquid phase, they're doing their best. They're trying. Now, if you have a stronger dipole, what would a stronger dipole entail? That would mean that the delta electronegativity is higher. So if I had two atoms that had very different electronegativities, but still made a covalent bond, they would have a very high dipole, very strong dipole. And as that increases in magnitude, as that increases in magnitude, the intensity of these attractive forces would also increase. And thus, as a result, the boiling point would go up as well. So, boiling point and vapor pressure are consequences of these intermolecular forces. So, intermolecular forces depend on the strength of the polarity in the molecule. And we talked about polarity in Chapter 5. You can review those lectures if you need to. Just go to the lecture playlist and click on the one that you need. If the dipole forces are strong, i.e. the dipoles in the molecules themselves are strong, then this attractive force increases and the boiling point will go up for that particular liquid. Now, there is one particular arrangement of molecules that tends to be more effective in terms of its intensity of interactions. And one of the features that is required of this specific dipole interaction is that the molecules are small. Small molecules have less distance between each other. I can't get this to select. Why not? There we go. The smaller the distance, the stronger the attraction is. So if you can make your molecules small and have a strong dipole, you have a good recipe for molecules that will stick very well to each other, and thus have a high boiling point. An example of this would be if you take your magnet on the fridge. We're going to just use this fridge magnet analogy and abuse it to death because it's a good analogy for this purpose. If you hold your magnet like 2 feet away from the fridge, you don't feel any attraction, right? Like if you let go of the magnet, it'll just fall to the ground. It won't get attracted to the surface of the fridge. There is an attraction, but it's very, very small, propagating over that much distance. Now, if you slowly approach the fridge with the magnet, at some point it will try and stick, and you actually feel the force of attraction pulling the magnet towards the surface of the refrigerator, right? So as you get closer and closer and closer, it becomes harder to keep the magnet away from the fridge and resist its ability to just pull out of your fingers and snap to the surface. So distance affects these types of interactions. And the smaller that distance is, the stronger it is. So what can we possibly do to make the most powerful interaction we can think of? Well, we've already described one idea, and that is to make the molecule as small as possible. And then the second idea would be to make it have the largest dipole that we can. It still has to be covalent, because if it turns ionic, then we don't have intermolecular forces anymore. We have actual bonds, because we have ions. So let's optimize those two features. Make the molecule as small as possible and make its electronegativity difference, in other words, its polarity, as big as possible. And that's where you get this type of interaction. This is called a hydrogen bond. Whereas the previous interactions on this slide were just any dipoles that we want. That's why they're called dipole-dipole interactions. I don't know if I actually said that, but there you go. Hydrogen bonds are a special type of interaction. They are not bonds. This is a misnomer. This is a really stupid name that chemists have chosen, particularly to confuse Chemistry 121 students. So be mindful of this. A hydrogen bond is not actually a bond. It is just a very strong attraction. Now, this particular arrangement of atoms satisfies our criterion. One, the bonds are extremely polar, because the difference in electronegativity between the elements is very, very high. And two, we have minimized the distance between the two molecules, because we're using hydrogen as our sort of like in between. Hydrogen is very, very small. One proton, one electron can't make it that big, right? That allows us to put the positive part of the molecule, which is the hydrogen, real close to the negative part, which is whatever the other thing is on the molecule. I did that backwards. Look at me. Don't pretend you're not looking at that one. There we go. and so on. There we go. And so this distance is very small, and this electronegativity difference leads to a large dipole on the molecule. Oh my goodness. Oh, that's what I heard. The cats are fighting. Stop that. No, don't look at me like that. What is wrong with you? They're both looking at me like I'm the one who's being a jerk. All right. So this type of interaction, the hydrogen bond, only forms under certain criteria. We need to have a very small distance, and we need to use a really tiny element to do that. And the only element that qualifies for that description is hydrogen. So step number 1, you have to have hydrogen. Duh, it's a hydrogen bond, right? You gotta have hydrogen. Step number 2 is that you need to have one of these 3 elements, the most electronegative elements we can get our hands on, that are also small. Nitrogen, oxygen, and fluorine. And then the last step to make a hydrogen bond is once you have all these pieces, you need to have them arranged in the following manner. I'm going to just call this X for now. The arrangement that you need to have for a hydrogen bond to occur and we're just going to draw bonds or whatever. So here's an atom X of a hydrogen bonded to another X, which whatever is going on over here, we don't care. And so what we need to do is we need to have H bonded to X and it has to be oriented at the electron pair, the non-bonding electron pair on another X. And if you can do that, then the interaction that you've made is a hydrogen bond. And so you can see this criterion in action here. I have H, which is bonded to a very electronegative atom, pointed at the electron pair of another very electronegative atom. And those elements that are allowed to be X are N, O, and F. You cannot pick any other elements because their electronegativity is either not high enough or they're not small enough. Chlorine, for example, has a very high electronegativity. Its electronegativity is 3.0. That's the same as nitrogen. But chlorine won't form hydrogen bonding because it's too big. You don't get a good enough interaction. We need something smaller. All right. So now you should be able to identify whether a molecule has a dipole by determining if it's polar or not, or if it can potentially make a hydrogen bond by seeing if it fulfills these criteria. All right. Now, down here, where I say H is trapped between the two N or F, remember it's got to follow it's got to fill these criteria. So remember that H has to be bonded to one side. And it's got to be pointed at the electrons on the other side. Since you can't make 2 bonds to hydrogen. But what we're trying to do is we're trying to approximate that. If we could make 2 bonds to hydrogen, it'd be something like this, right? All right. So that's what I mean on there by it's trapped between these 2 elements. I don't just mean spatially in any orientation you want. It has to specifically be like this. All right. There's our hydrogen bond circled there. What I want you to do is I want you to try and draw the Lewis structures of these molecules. So CH4, H2N, and H2, CH3F, and H2S. And once you have drawn those Lewis structures, I want you to try and see which ones could hydrogen bond with themselves. So what that means is that draw one of these molecules, then draw a second one. Can you hydrogen bond in any possible way? I'm going to just put a little bar between these. What you should immediately be able to do is eliminate at least half of these by saying, oh, I cannot form a hydrogen bond with these. And then say why or why not. And we'll go over the answer in a second for that. But I'm going to give you like 5 minutes to draw these Lewis structures. And if you can form a hydrogen bond between a molecule and another copy of itself, try and draw that on your paper. We'll go over the answers in about 5 minutes. All right, 1 or 2 more minutes, and we'll draw out the answers, and then we'll take our break because we're due for that. All right, let's go over the answers here. So I'm going to quickly draw the Lewis structures for all of these molecules. Oops, that's scrolled up a little bit too far. Oh, not only that, it went all the way to the left, which is not helpful. There we go. Okay, so we're going to draw the Lewis structure for CH4. All right, can CH4 hydrogen bond with a copy of itself? And the answer is no, because there are no nitrogens, oxygens, or fluorines, right? So no, I cannot cause a hydrogen bond with CH4. So that's great. Let's move on. All right, there's H2N and H2. If I was to make a hydrogen bond here, I would first need to have an N or an O or an F, and I have that. So this qualifies. And then I need to make it such that I have a hydrogen bonded to a nitrogen pointed at the electron pair on another nitrogen. So I could do something like this, actually. And so this right here would be my hydrogen bond. Because I have my hydrogen connected to a nitrogen through an actual bond pointed at the electron pair on another nitrogen. And so this would be my hydrogen bond. And so it is possible for that to make hydrogen bonds. All right, what about CH3F? Now there's an F in there. But my fluorine is not bonded to a hydrogen. If I don't already have a covalent bond to a hydrogen, I can't possibly fulfill that part of the criteria, right? I cannot point the H that is bonded to my fluorine at the other fluorine because that bond doesn't exist. There's a carbon there, right? So I cannot hydrogen bond using this molecule. And then finally, H2S. Same reason as before. I can't form a hydrogen bond here because I don't have any N or F in this molecule. So the only one that could hydrogen bond was the second one up here. All right. Now I'm going to leave that example on the screen here for a second because what we're going to do is we're going to take a break. And if you'd like to try it while we're on the break, you can do so. Otherwise, we'll come back in 10 minutes. I do need to get the timer on the screen here. Where is the timer? There it is. All right. So go ahead and take a 10-minute break. I'm going to put the music back up. The music this week is Final Fantasy VI, which is probably one of the most important video games for me personally. And it is re-released as the Pixel Remaster tomorrow. So that's what I'm going to be doing on Wednesday night, is playing one of the earliest games from my childhood. So enjoy some of the music from the Super Nintendo version during our break. I'll see you in just a little bit. Alright, we're back. Alright. I can't wait to hear all of these tracks, like, completely redone, like, by a really talented orchestra tomorrow. If you haven't played any of the Final Fantasy games, you can get them on Steam. They just re-released the first 5, and the 6th one is being re-released tomorrow. And all of the music has been redone, and it's the music is probably the most amazing part of it. It's so well done. And I would love to play the. I mean, I guess technically, since I will have it downloaded tomorrow, I could play it, but I just don't want like the channel to get a copyright strike. Like, why are you playing this music? This game just came out. They tend to be kind of harsh about that. All right, down at the bottom here, we're going to draw hydrogen bonding that can occur in these situations by mixing different molecules together. So normally, when I ask you a question about what type of bonding will occur, the assumption is that you're looking at just that one single type of molecule. So in the above situation, we assumed that the only molecule in each of these liquids was the one we were working with, and that a pure solution of this, which is called, I believe, what is this called? I don't know what it's called, what its systematic name is. It's some sort of diamine, or diamine, or whatever. I was going to call it ethylamine, but that's not what this is. I don't think, anyway. So what we can do here is we can draw hydrogen bonding interactions between any two molecules that we want to. However, I have to specifically tell you that that is what we're doing here. So in this case, we're going to be looking at water and ammonia. That didn't capture properly. Let's fix that. And so what we need to do is we need to draw both molecules and see if the opportunity for hydrogen bonding arises. So first we'll draw ammonia, and then we'll draw water. Is there a way that we can fulfill both criterion? So do I have hydrogen bonded to a nitrogen, oxygen, or fluorine? Turns out, yeah, all of these bonds qualify. So I can take any bond and point it at an electron pair on the opposite atom. And it turns out I could do this in any number of ways. So if I had this doing this, I'm going to spin this guy around. Hit the wrong button, or drew the wrong thing there. So this would be my hydrogen bond. However, I could also instead do something like, say, this. And then I get a different molecule. And a different arrangement. And so in both cases, I can make a hydrogen bond using different parts of the molecules. It doesn't really matter which orientation you do. That's more of a curiosity. As long as the molecules stick together, the effect is the same, right? Now, something that we can indicate, and this is a little beyond the scope of this class, however, it might be helpful to you in biology to know this terminology. Whatever molecule has the hydrogen with a covalent bond to the nitrogen, oxygen, fluorine atom, we're going to call that the H bond donor. And then whichever molecule has the electron pair that that hydrogen is pointed at, we're going to call that the H bond acceptor. Some molecules are only H bond acceptors. For instance, if I draw formaldehyde down here, here's what formaldehyde looks like. Carbon, oxygen, hydrogen, hydrogen. Now, I have no hydrogen connected to an NO or an F through a covalent bond, so I cannot make hydrogen bonding with formaldehyde by itself. So a solution of just formaldehyde in it would not hydrogen bond to itself, and its boiling point would not be as high as you would expect it to be. But if I mix this with something else that had a bond, this could be an acceptor for H bonds. So things with only the potential to accept hydrogen bonds do exist. And this is going to become a very important concept later on when we talk about solubility. So this is chapter 8. So we're going to come back to this bonding notion for more than just boiling point in this class. Okay, so that's what that discussion is intended to be. The next one, HF is mixed with HCl. What ends up happening here is these two sort of look at each other. And this is not a polar enough bond. My HCl does not form hydrogen bonds. So this molecule sort of just toodles off and does its own thing. But if I have another hydrogen attached to a fluoride here, I could form a hydrogen bond in this manner. So in a solution of HF mixed with HCl, the HFs will all stick to each other and they will remain a liquid, whereas the HCl might evaporate. In other words, these two would exclude each other, is what we would predict. And this is a phenomenon that we're going to notice happens with fairly high frequency when we talk about solubility in chapter 8. All right. On this diagram here, I am showing the weight of a molecule in grams per mole. So let's write that down here at the bottom so you know what that means. And on the y-axis, we have the temperature in Celsius. And what you probably can tell is that as the mass of a molecule increases, its boiling point tends to increase. We're going to discuss this feature coming up. So this is actually a very well-known property. I don't know why the pen did that. Wow, okay. Apparently, PowerPoint does... Hold on just a second. Apparently, PowerPoint has given up on any attempt... There we go. To try and draw properly. So in the next slide or two, we're going to talk about how mass is related to boiling point in just a second. And it's probably not in the way that you think. But you'll notice here that where I put the little question mark is where water should go if the only thing affecting boiling point was its mass. So if at 100 degrees Celsius it was boil at like negative 100 degrees. Oh, excuse me. And that would make for a very chilly shower in the morning, right? The reason that water has such a high boiling point is because water can stick to itself extremely effectively through hydrogen bonding. And so, water molecules stick to each other effectively, and it pushes their boiling point up way higher than we'd expect, by 200 degrees Celsius, from negative 100 to positive 100. And it's because of this interaction that all life is possible. It's due to hydrogen bonding. I mean, it's due to other things too. But hydrogen bonding is very, very crucial because without hydrogen bonding, you could not have liquid water at a reasonable temperature. On the screen here, I have a picture of ice and how ice crystallizes. Ice is liquid water cooled down to a temperature such that it solidifies into the solid state. And on the screen here, you can see just how these molecules are arranged. And they're all arranged in such a way that they form hydrogen bonds in a very regular looking lattice. And if I zoom in on just one of those, that looks like this. Again, don't worry about the numbers. The numbers aren't important. But what is important here is that the distance for the hydrogen bond is very, very small. Which means that it is much stronger than any other. It's much stronger than any other intermolecular force due to it being very polar and having a very short distance between the dipoles. Isn't water known as a sticky liquid? I have never heard of it called that. You might be thinking of viscosity, in which case water actually isn't that viscous because it's too tiny. Do we talk about viscosity in this class? I don't really talk about viscosity that much. Viscosity is the ability of molecules to get tangled on themselves and resist flow. So something like water, when you turn on your faucet, water just pours out of it very quickly. But it doesn't really stick to other molecules enough that it slows down. And that's not due to intermolecular forces. The water molecules stick to each other very well because they have surface tension and stuff like that. But if you look at like something like syrup, like if you open a bottle of syrup and you invert it and you don't squeeze the syrup out, it pours out rather slowly, right? Like the expression thick as molasses exists for a reason. And the reason that molasses and syrup and stuff like that flow so slowly is because the molecules do all stick to each other, but they also tangle on each other and inhibit the other molecules' ability to move past each other. The best example I could think of is like walking through a giant like spider web. Like a really, really big spider web that like covered an entire like door. Like you get stuck to it and it would inhibit your movement. It'd be very hard to go through it. And that'd be because everything is stuck to itself in the web. No spiders in the web, just the web. Because spiders are terrifying. We don't need to worry about spiders. Nothing makes webs that big. Geez, Wes, what is wrong with you? Let's move on. I'm using that because I play Dungeons and Dragons, and web is a really good spell, but spiders are not really good things. I am an arachnophobiac. I do not like spiders. Or insects at all, actually. I can deal with some insects, like a ladybug or a butterfly or a dragonfly. Like some insects are okay, but like wasps or bees, not a fan. Spiders, not a fan. I can deal with tiny, tiny spiders. That's about it. All right. Up to this point, we've considered polarity as an attractive force. Delta plus and delta minus attract to each other and cause an interaction that we call an intermolecular force. What happens if you have atoms or molecules that are nonpolar? Can they generate a dipole? Well, by definition, no, they can't, right? They cannot create a dipole because they are nonpolar. However, there is an opportunity to create a temporary dipole. And that interaction is shown above here. If I have an atom of anything, really, like for example helium, we use this, and my electrons orbit in random chaotic paths that eventually takes them around the entirety of the atom, then at any given time, I could have both of my electrons on one side of the atom, and the other side does not have any electrons at all. In other words, the nucleus would be exposed, and something else looking from the outside could see it, right? So in other words, what this means is that because of my electrons are being on this side, I could say, okay, this side would be delta minus, and this side would be delta plus. And so even though I have a temporary, or I have a molecule that's nonpolar, it can get this state based on where its components are. Now, what happens if my electron moves back over here? Well, the second that it does that, this goes away and the effect is removed. It no longer exists. So in other words, at random intervals, nonpolar molecules will form temporary dipoles. And these temporary dipoles will attract to each other, and this is called the London force. So the London force is basically the same thing as a dipole, but much, much weaker because it only occurs randomly. For a dipole-dipole interaction or a hydrogen bonding interaction, those dipoles exist permanently. The electrons are permanently shuffled from one side of the molecule to the other due to electronegativity. But in nonpolar molecules, the only way you can get a dipole is if the electrons randomly create one. As a result, the attractive forces are much, much weaker. It would be like if your magnet was rapidly turning on and off. Like if you had an electromagnet, it wasn't working properly because there was a short in it or something. So it was only creating an attraction like every 30th of a second or whatever. I don't know. There would be a slight attraction, but it wouldn't be as strong. All right. Now, I hate this next picture, but I really just don't know of a good one. What this picture is showing here is that if I have a delta minus on one side of the molecule, because all of my electrons are over there, and I have a delta plus on an adjacent molecule, they will attract to each other, just like it was with a dipole. But because these are randomly created, the attractive force is much weaker. And so we call that attractive force the London force or the dispersion force. Either one's fine. Now, like we said, the definition of a London force is just, hey, my electrons are not distributed evenly, and that creates a temporary dipole. How do we make temporary dipoles more effectively? The property that we measure is called polarizability. This is just how easy can temporary dipoles be made. And the answer is, if it's very easy, then the molecule has a high polarizability. That's what the word polar means, right? Uneven distribution of electrons. If something is polar, the electrons move to one side. If I can polarize something, I can change where the electrons tend to be. There are two properties that are going to affect polarizability. And those two properties are, one, how many electrons there are. If there's more, it's easier to move them around, right? And then the shape of the molecule also matters. We're going to talk about shape very briefly in just a second here. First of all, if I have more electrons, so if I have something that has 6 electrons around its nucleus versus something that has 12 electrons around its nucleus, in order for me to get an uneven distribution of electrons, I would have to move most of my electrons to one side, right? But with something like this, to get an uneven distribution of electrons, it's more likely that this is going to happen just by virtue of there being more electrons. All I can do is move one over, right? 1 or 2 or 3. And the odds of that happening are increased if you have more electrons. If I have 100 electrons, what are the odds that 3 of them are going to be on the same side? A lot better if I could just pick any 3 and there's 100 to pick from. Certainly a lot better than if I only had 3. So as a result, the more electrons you have, the more likely the molecule can be polarized and create a temporary dipole. So what that means is that atoms like neon have very, very weak dispersion forces, or very, very weak London forces. And as a result, the boiling point of neon is extremely low. It's like 40 Kelvin or something like that. Xenon has a much higher boiling point. It's more like 180 Kelvin, I want to say. So if you are just counting the number of electrons, you can figure out roughly what the magnitude of the dispersion forces are. What if you're looking at two molecules that have the same mass? Then what we're going to care about is the shape of the molecule and how that shape affects polarizability. So I'm going to put two shapes on the board here. These are both molecules that have this formula. And if I was going to count the number of electrons here, the total number of electrons would be 42. Because each carbon gives you 6, so that's 30. 6 times 5 is 30, and then plus 1 times 12 for hydrogen is 42. Now I'm counting total electrons, not just valence electrons. That is the total number of electrons in that molecule, because we just care about where they are relative to the nucleus. If they have the same number of electrons, then they would have the same polarizability with regard to how many electrons are available to push around. And so they would probably have the same intermolecular forces, you would assume. But surface area also contributes. If I have molecules that are arranged in an oblong fashion, kind of like a hot dog here, and this is the region in which these two molecules can interact with each other, I could potentially put dispersion force interactions all along this. As long as I have a local area that has more electrons than the other, that will induce a dipole on the other side that would have less electrons, for example, and there'd be an attraction. And so I could do all these attractions along this area where these molecules touch. Over here for the spherical versions, this is a little bit harder because there's not as many places. The analogy I like to use for this is you can think of Velcro. Velcro is more effective if you have like two large patches of Velcro that stick together, right? As opposed to a tiny, tiny, tiny space where you just touch two pieces and have them stick. The key factor is surface area. The higher the surface area is, the more polarizable the molecule is, and the better the molecules will create dispersion forces and thus stick. Velcro is the same thing. If Velcro has a higher surface area, that means you have more opportunities for little hooks on the Velcro to hook to other hooks, right? And thus the interaction you get between the two things is stronger. And so you could see here, the boiling point of the linear version versus the circular or spherical version is different by a factor of like 20 degrees. That's not a factor, sorry. It's just different by 20 degrees, 25 or so. So all that changed here is the shape. So again, our factors that are going to matter for dispersion forces are how many electrons are there, and then in the case of two things with the same number of electrons, the larger the surface area, the higher the interaction of the intermolecular forces. Now, counting electrons is tedious. So instead, just consider molar mass. Because if we say that, oh, as the molar mass increases, so does the number of electrons, then you don't have to sit there and count electrons and go, okay, well, each carbon is 6 total, plus each hydrogen is 1 total, plus each platinum is 94 total, or whatever. 70, I don't know. You don't have to do that. You don't have to count all those. You could just look at the periodic table and say, oh, this one's further to the right. Or further down. It has a higher mass. Or you just look at the mass number at the bottom. It's bigger. Molar mass is easy to calculate. You just type it into Lentech. So the higher the molar mass, the more easily polarized the molecule is, and thus the stronger intermolecular forces it has. And if we go back to this slide, there we go. Now we can explain why these are sloped up as they are. Those molecules down at the bottom, CH4, SiH4, GeH4, SNH4, totally nonpolar. The only way they have to interact with other molecules of their type, for example, CH4 and other CH4s, is dispersion forces. And because CH4 doesn't have that many electrons, it doesn't have very much dispersion. SiH4 has more electrons, so it has a stronger dispersion. GeH4 has even more, and so on and so forth. And so that's where the trend goes in this linear direction upward. Where we can say, oh, as things get heavier in terms of their molar mass, the stronger the attractive forces come between them. That's going to be really relevant to you in biology when you're talking about things like lipids and fats and stuff like that. Because this is how cell membranes hold themselves together, is they do it through dispersion forces. There we go. Now, all molecules have electrons, so all molecules have dispersion forces. So everything has dispersion forces. Dipole forces and hydrogen bonds are different in the sense that they are not everywhere. If a molecule is nonpolar, it cannot have a dipole force. Now, because dispersion forces are random, they're usually the weakest. So if you have a choice between dispersion and dipole-dipole, dipole-dipole is going to be the interaction that is stronger. What that means is that I will ask you questions about which is the strongest or most significant intermolecular force in this molecule. And you'll have to answer either London dispersion, dipole-dipole, or hydrogen bond. And so you're going to have to check which forces are available in the given molecule. London dispersion is easy. Everything has it. So if you don't have anything else, you just say that and you're done. Now, if you make the molecule big enough, so like real big, like molar mass of thousands of grams per mole, make it humongous. Then what ends up happening is that because there are just so many electrons, dispersion forces become more significant. And in fact, they can become dominant in large molecules. Remember how before we said for the dipole-dipole interaction or hydrogen bonding, we wanted to make as small and close an interaction as possible? With dispersion, it's the opposite. We want to make as big an interaction as possible. Because the larger the molecule is, the more opportunities and locations there are to create dispersion forces. Whereas dipoles are just fixed around whatever part of the molecule is polar. So with all of this in mind, we're going to make one last little chart that's going to be helpful for us. All right, and here's what that chart's going to be. So on the y-axis, we're going to put strength. You know what I could do? I could just tilt the tablet sideways here. Oh, now it's oh, this is super disorienting. Never mind. I was going to try and write sideways, but that's not going to work. All right. We're going to put the strength of the intermolecular force, and on the x-axis, we're going to put molar mass in grams per mole. All right. So we said that dipole-dipole was stronger for smaller molecules and weaker for bigger molecules. And we also said that hydrogen bonds were extremely strong, but only if they were small and very polar. Dispersion kind of does the opposite. It starts off real weak, and then it gets significant. As molar mass increases. So we're going to call this region low molar mass, and this region high molar mass. Okay? We're not going to care about the middle part in here where everything is kind of the same. I'm not going to give you a molecule and be like, surprise, this one was bigger because you had to look it up. Because at some point, that's really all you can do. So what I am going to do is I'm going to call a molecule either low molar mass or I'm going to call it small. Or I'm going to say it has a high molar mass and call it large. And so your task would be to arrange various small molecules by their likely boiling point. And so I might give you a molecule that has a hydrogen bond in it, a dispersion force, and a dipole-dipole. So 3 different molecules, each one has that one force in it that's primary. And I might say, sort these by their boiling point. And so you would arrange them by saying, okay, well, for a small molecule, hydrogen bonding has the highest boiling point, then whatever has dipole-dipole, then whatever has dispersion. And then for a high mass molecule, dispersion would have the highest boiling point, and then hydrogen bond and dipole-dipole. So those are the types of questions that you'll see in the Chapter 7 quiz, which I'm going to put up on there tonight, because I guess we're done with the chapter, aren't we? Yeah, we have like 2 more slides. All right. So I'm going to give you these two molecules, and what I want you to do is consider each of these statements. Which of these has a stronger dipole-dipole force, and which of these has a stronger dispersion force? Note that we're not talking about the boiling point or whatever. I'm just trying to compare these specific types of forces. So go ahead and try and predict the answer for this in the chat, and we'll go over the answer together in just a second. All right. In order to figure out which one has the stronger dipole forces, you got to draw the Lewis structures for them. So we'll do that. So there's CH3I. I don't know why I drew that one first. That's okay. And there's CH3F. So if I wanted to figure out which of these was polar and which one was nonpolar, I'd have to go look up their electronegativity. So this is very polar. Oops, this is 2.5 actually. I don't know what the polarity of iodine is. I think it's very similar. So P table, and I want electronegativity. Iodine is 2.66, which is virtually the same as... So I would say that this side of the molecule is delta plus, and this one's delta minus, and this one is essentially just nothing. So, which is the stronger dipole-dipole? That's going to be this. Now, of these molecules, which is the stronger dispersion? That's going to be which one has a higher mass. Well, iodine is much larger than fluorine, so that's going to be this one. Now, the next question we could ask is, which one has the higher boiling point? And it turns out that that's very difficult to predict, because CH3F is a small molecule, and CH3I is a large molecule. So, which one is bigger in which case? And the answer is you just have to do the experiment. So, this is not something that you can easily predict. So, I won't ask you a question like that. I will ask you to just make a guess with the information that you have and ask you about basic concepts. All right. So there's our summary. Which intermolecular force is stronger in a molecule depends on several factors. It depends on the size and the mass of the molecule, the surface area, and all sorts of stuff. For tiny molecules, remember that dipole forces and hydrogen bonding will be the stronger forces. But for really large molecules, dispersion forces take over and become the winners, basically. For a thing like a lipid, which is a bunch of fatty acids connected to a glycerol, so that'd be a triglyceride, actually, which is a lipid, but the molar mass on those things is very, 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 very large, and as a result, they have very, very good dispersion forces. So cell membranes are pretty much all just London dispersion forces. And that'll become very important in biology, so try and remember that. All right. We are out of time. But what I want you to do is look at these two problems tonight as you are reviewing the material. On the screen there, I have a solid, a liquid, and a gas for each of these hydrocarbons. And you should be able to tell me which one is the solid, which one's the liquid, and which one's the gas at room temp. And then you should be able to draw the interaction for those things down here. So I'm going to quickly just draw ethanol in case you want this. There's ethanol. I could draw it like that. And what we're going to do is when we come back on Wednesday, because we have lecture tomorrow, because there's no lecture yesterday, we're going to start Chapter 8, and we're going to talk about these interactions a little bit more when we talk about solubility, which I believe is lab number 4. I think 4 is solubility. No, 4 might be like radioactivity lab, which sort of exists on its own. All right. But that's it for Chapter 4. Or not Chapter 4, I'm sorry. Chapter 7. Let me do this so that we can get our little woohoo here. Oh, there's the homework practice. Right over the ethanol. Good job, me. So 91 through 106. And then, of course, hooray. All right. And that's all I got. So when we come back tomorrow, we're going to do Unit 8. Unit 8 is solubility. It will probably go pretty quickly. We might even finish it tomorrow, or at least get real close. There's actually not much of the class left to do, believe it or not. Chapters 8 and 9 go fairly quickly. Chapter 10 is a little bit more involved. But yeah, we're almost done with the class, believe it or not. I mean, we're already 7 weeks in. This is week 8, so surprising nobody. Blink and you'll miss it, I guess. That's all I got. So tonight, make sure that you finish Chapter 6's quiz. It will close. I will put the quiz for Chapter 7 up soon. And we'll see you tomorrow. Have a good one.